Welcome to lecture. We'll get started in just a minute or two. So we're finishing up the stoichiometry type chapter, and then we'll be rolling into the gas chapter, which the notes again are online as well in their normal source spot with all the other notes. So we'll get started in just a minute or two. And as always, again, if you do have questions, please feel free to ask them down below or wherever that is, I guess, on your screen in the chat box. And again, we're going to pick up where we left off last time in lecture, and then we will roll into the next chapter, which is, I think, chapter 8, and gases. All right, so again, we're picking up here in that kind of stoichiometry, molarity handout, which again does cover sort of parts of different chapters. I think some of 5 and maybe some of 6 and maybe even some of 10, if I'm not mistaken. So last time we sort of finished up talking about concentration. We talked about molarity, which again is a most sort of common unit of concentration, and that's big M, and that is moles of solute over liters of solution. We also saw and talked about dilution, and we had the dilution equation, which most people use in this version here, which is M1V1 equals M2V2. And where M1 and V1 is typically the more concentrated solution, while M2 and V2 is typically sort of the more dilute solution. M1 and M2 being the molarity of each of those solutions, V1 and V2 being the volume. Again, volume can really be in any units, milliliters or liters, is common units that are used. And although we do use M1V1 equals M2V2, and that again is because, as we talked about, molarity there is our sort of most common unit that we use. But technically, you could use other concentration units, some of which we'll talk about here in just a second. It doesn't necessarily have to be molarity, but it can be. Remember, though, that if we use molarity by itself and we want to find something like moles, you do need to convert the volume into liters. That way the units will properly cancel out, and what you'll be left with is moles. Remember that if you do multiply milliliters times molarity, what you get is not moles, but you do get millimoles. And again, you would need to divide by milliliters. So in the dilution equation there, again, we can leave it in milliliters in terms of the volume on both sides. And it works out okay because, again, technically, if you take milliliters times molarities, you get millimoles. And then if you divide that millimoles by milliliters, the milli part of it cancels each other out, and you actually get yourself back to moles per liter. But again, if you're kind of doing a standalone sort of problem where you're just using molarity and volume, you do need to convert the volume into liters when you use it with molarity. Again, otherwise you won't get actual moles. You'll get that millimoles. And we sort of did some solution stoichiometry problems, which is really like basic stoichiometry problems. Could be a limiting reagent problem as well, but basic stoichiometry problems, the main difference is a lot of times at the beginning of the problem. So instead of using grams and molar mass from the periodic table like we do a lot to get moles, we oftentimes will use that common relationship that we talked about, the liters times the molarity, which is moles per liter, to get us to moles, to kind of start the stoichiometry process. And the other difference is usually at the end, something with molarity is involved. So a lot of times we may take the moles and divide by the molarity to get liters. Or we may be given like the liters and you get the moles and you could get the molarity from it. So in sort of a solution stoichiometry problem, usually again, the major difference there is going to be our volume and molarity, and that's going to allow us to get to moles. And then at the end, somewhere along the way, usually at the end, you have to use molarity again. We also talked about more specifically titrations, which are really just solution stoichiometry problems. Remember, in a titration, we add a certain volume, especially like in a acid-base titration, for example. We add a certain volume of, say, base to the acid, and we typically will titrate it until we reach what is known as the equivalence point. At the equivalence point in an acid-base titration, that means that we have hit the point where exactly equal moles of acid and base are there at that point, which means we pretty much use up all the moles of the acid and all the moles of the base because they're equal to each other at that point. And that typically is where we want to stop our titration, is when we do hit that equivalence point. That's usually done or indicated by an indicator. And again, a common indicator, which is phenolphthalein, which we talked a lot about, and will also be part of the titration experiment that's coming up, is one that's commonly used. And indicators typically work over a pH range, and they typically will change color over a specific pH range. So something like phenolphthalein, for example, works on a pH range of like 8.3 to a pH of 10. And in acidic solution and neutral solutions, something like phenolphthalein is colorless, but does turn a pink color in that basic area. And a basic solution is a pH above 7. So with it working between 8.3 and 10, at the 8.3 area, it's kind of colorless to super light pink. And then as you head towards a pH of 10, it gets very darker pink. And usually when we use something like phenolphthalein, the reason we use it is, and the reason you would use any specific indicator when you do a titration, is you would use it to be able to know when to stop at the equivalence point. And that means you should always pick an indicator that will actually change color around your equivalence point. So you just don't want to pick an indicator that you won't see a color change. You want to be able to kind of see that color change as an indicator that you should stop the titration. And when you do a titration, you essentially know the molarity usually of one substance, and you usually know, for example, how much volume of that substance that you use. So because you know the volume and the molarity, that will allow you to get the moles of whatever you added. And then you could do a stoichiometry problem to figure out the moles of your unknown. And then depending on what you're looking for, you may be able to calculate the molarity of your unknown by putting them together. Again, if you happen to have had the molarity, which is usually not the case in the titration, you can figure out, obviously, the volume as well. Any questions on that stuff that we talked about, I think, last time? All right. So again, like I said, molarity is really the kind of most common unit of concentration that we come across. But there are other units, and a popular sort of unit, I don't know, popular is the right word there, but a common unit that's sometimes a percentage type unit is percent mass to mass. And that is sometimes abbreviated like this: percent M/M. And that is percent mass to mass, is basically what the two M's stand for. And the percent mass to mass is the mass of the solute divided by the mass of the solution. So we're basically usually taking grams divided by grams, and then you times it by 100%, and you get a percentage. Now, the important part of this calculation, and where people mess up a lot, is the bottom part. So remember that when we talked about a solution, it is made up of two things. It's made up of the solute, which is the smaller part of the solution, And it's also made up of the solvent, which is the larger part of the solution. And what that means is on the bottom, you want to make sure that you get the mass of the solute and the mass of the solvent, and you want to make sure that you add those together. And the reason I say you want to make sure in these type of problems is it is very, very common that those numbers are given to you sort of separate from each other. So in the problem, they'll give you the mass of the solute, they'll give you the mass of the solvent kind of separate. And very often people will just use the solvent instead of actually adding them together. So unlike a lot of problems, this type of problem, you typically need to add those things together to actually get the mass of the entire solution and not just use the solvent. Now, percent mass to mass is like we see down there, the mass of the solute over the mass of the solution times 100%. There's also some other sort of percent concentrations. So I've got a little bit of room here. We'll kind of write them in. There's also one that is percent volume to volume, like an alcohol perhaps. And that is the volume of solute over the volume of solution times 100%. So very much kind of the same idea, except here typically it's milliliters over milliliters is what you're looking at. And there's also a percent one that is percent mass to volume, which means it's the mass of the solute divided by the volume of solution times 100%. So these are three sort of very common sort of percentage concentrations. Out of all three of these, really this one here, the percent mass to mass, really is the one that you do have to watch out for in terms of the bottom part. On the other ones, since it's the volume of solution, that typically is just sort of given to you, so you don't have to necessarily, they usually won't, not to say that they can't, but usually they won't say, hey, here, this is the volume of the solute and the volume of the solvent. They usually will just straight out give you the volume of the solution. So you don't have to worry about that bottom part so much in the other percentages, but you definitely do in the mass. So what does that mean when we have one of these? You can do these problems using these formulas and really just sort of plugging and chugging them in there. But you can also sort of use these guys if you're given a percentage as sort of a usable conversion factor. So for example, if I had a 4.5% mass to mass solution of sodium chloride, remember as well as we talked about that the name of the solution is really the solute. So the solute here would be sodium chloride. The solvent would be something like water. What that means is we technically would have 4.5 grams of sodium chloride in 100 grams of solution. If we want to kind of convert it into a conversion factor and do maybe a dimensional analysis type of problem, you could also use it in the opposite fashion with the 100 grams of solution over 4.5 grams of sodium chloride. You would do the same thing if you had a 4.5% volume to volume sodium chloride solution. You could say there is 4.5 milliliters of sodium chloride in 100 milliliters of solution. Or you could do the opposite. In 100 milliliters of solution, there is 4.50 milliliters of sodium chloride. And lastly, if you have the 4.5% mass to volume sodium chloride, you could do the same thing, except this would be 4.5 grams of sodium chloride in 100 milliliters of solution, or in 100 milliliters of solution, there would be 4.5 grams of sodium chloride. So sometimes it's a little bit easier if you have sort of the percentage given to you to sort of convert it into like a conversion factor. Obviously, in each of those cases, we assumed 100. The reason we assumed 100 is because it keeps the numbers the same. You could technically assume 200 if you want, but you have to double everything. So obviously we usually assume when we have a percentage, we have 100 of it. So let's take a look at one here. So why don't you take a minute or so here and calculate this. We're looking for the percent mass to mass of the solution. So calculate the percent mass to mass and see what you come up with, and we'll talk about it here in a minute. All right, so let's take a look and see how we're doing. Again, we're looking for the percent mass to mass, which is the mass of the solute divided by the mass of the solution times 100%. So when we're mixing 2.5 grams of calcium chloride with 50 grams of water, what we know is, again, the smaller part of the solution is going to be our solute. So our calcium chloride in this case would be our solute, and our solvent would be our water. And that's a good solvent because that's an ionic compound, so it works well, which means that the mass of the solute will be the 2.50 grams. The mass of the solvent would be the 50 grams. And again, that is not the mass of the solution, though. That is, again, just the solvent. So to get the solution, we need to add those together. So the mass of the solution would be our 50 grams plus our 2.5 grams, gets us something like 52.5 grams. So again, it's very common that people will just use the mass of the solvent, and they would divide by 50 in this case, which obviously would give you the incorrect answer. So we want to take our solute, which is 2.5. We want to divide it by our 52.5. Gets us something like 4.76%. And usually people will do the m/m to indicate that it's mass percent and lay up a little, not sodium chloride, I got that in my head. Try some calcium chloride. There you go. Question on that calculation there. So really important, like I said, out of those three, especially with the mass percent, to make sure that, again, you get the entire mass of the solution, not just the solvent. Any questions? So again, a reminder, if you do have questions, feel free to ask them. I will go back and answer them if you do need some help. If not, give this one a go here. Take a minute or so and see what you come up with. Okay, so again here we're dealing with the percent mass to mass. And in this case, we're actually given the percent mass to mass, which is 37.2%. We want to know what is the mass of the HCl. And if we have 35.5 grams, and that would be of the solution. So you may ask, well, how do I know that? It's the 35.5 grams of the solution. Remember that if this was a hydrochloric acid solution, the solute would be the hydrochloric acid. So since we're looking for the mass of HCl, that would indicate that this would have to be the solution in that case. And again, we can, if we want, solve this one of two ways. We could just plug and chug into that formula. Secondly, we could kind of write a conversion factor. So what that means is there technically be 37.2 grams of HCl and 100 grams of solution. Or again, you could do it the opposite way if you like. So I'll solve this problem more dimensional analysis type way. So if we start with our 35.5 grams of solution, we're going to use the conversion factor on the left there, which is 100 grams of solution, and 37.2 grams of HCl. The grams of solution will cancel each other out, and we will get something like 13.2 grams of HCl would be in that solution. Any questions on that? Again, if you plugged and chugged it into the sort of formula, if you will, the percent mass to mass is our mass of solute, mass of solution times 100%. In this case, we would be solving for the HCl, which is our solute. So basically, we would take the mass of the solution times our percent mass to mass divided by 100%. And that is essentially what we did here. It's really the same math. Again, one more sort of a conversion factor approach, one it's more of a mathematical approach. So math-wise, they're basically the same if you plug it in or do that. Any questions on percent mass to mass? Again, percent volume to volume, percent mass to volume pretty much works exactly the same way. All right, so let's talk about another concentration unit, which we sometimes come across and we may come across a little bit later on this semester. And this is what is known as molality, not molarity. So if you remember molarity, I'll do it like this, big M, yes. Molality is small m, yes. So also not to be confused with other m's that we come across like mass or anything like that. So when we calculate the molality of a solution, it is similar to molarity. It is the moles of the solute, but the bottom part is a different type of unit altogether. It's actually the kilograms of solvent. So molality, which is little m, is moles over kilograms of solvent, and again slightly different than molarity. Just like molarity is molar, this is molal is sometimes referred to. So if you had a 4.5 little m sodium chloride solution, what that means is you have 4.5 moles of sodium chloride and a kilogram of solvent, yeah, like water or something like that. So again, molality, not to be confused with molarity, is moles of solute over kilograms of solvent, which in a lot of cases they will give you the solvent, and you usually will have to do a conversion from grams to kilograms is a common one you have to do with the solvent. Sometimes they may actually give you the milliliters of the solvent, and what they'll also give you in that case is the density. So remember that density is mass over volume. which means you can find the mass by taking the volume times the density. So sometimes, they'll actually give you the volume and you need to calculate the molality, but they'll also give you the density with that, and that will allow you to get the mass of it. So those are the two sort of common ways that you could get to the kilograms of solvent. Any questions on that? So why don't you give one a go here and see what you come up with. We want to calculate the molality of a solution that's prepared by dissolving 61.7 grams of C₃H₄OH in 175 milliliters of water. Density of water is 1 gram per milliliter. So take a couple minutes here and give it a go when I go back there. That slide. No problem. Okay, so we are looking for the molality, which again, different than molarity. So our molality is our moles of solute over kilograms of solvent. So in this particular case, this here, this guy, that's going to be our solute. The water here will be our solvent. So we do have to do a couple conversions. Since we have our guy here in grams, we need to convert it to moles. So we're going to need the molar mass from the periodic table. So for C₃H₄OH, that's going to be 3 times 12.01 plus 8 times 1.008 for all of the hydrogens that are there, plus a 16 for the oxygen that is there. And if we do that, we end up with 6009 grams per mole. So again, the first thing that we need to do is 61.7 grams. We're going to convert it to moles using the molar mass from the periodic table. And looks like maybe 1.03 moles, I hope, if I punch that in right. We then need to get the kilograms of solvent here. We have the volume, which is 175 milliliters. So as I was just talking about, you oftentimes might need the density, which is not too bad in this case. Density is 1 gram per milliliter. So that will get us 175 grams of water. And we don't need it in grams, but we do need it in kilograms. So like 1,000 grams in a kilogram. So those are going to cancel. And basically just move the decimal place over 3 places. Gets us 0.175 kilograms. So now we got both parts here, and let's see how you did there. We got M would equal our 1.03 moles divided by our 0.175 kilograms. And we actually end up, I believe, with 5.89. The units here can be left as moles per kilogram, just like you can leave moles per liter for molarity, or you could write 5.89 and just put little m next to it, which would stand for molality. Any questions on any of those steps there? So molality is a unit of concentration, not used as much per se as molarity, but there is sort of one aspect where we do use molality a lot, and that is what is known as colligative properties, which we'll talk about in a later chapter. And the use of molality comes out a lot in those type of calculations. So we will see molality kind of pop up down the road in another chapter. And it is when we talk about colligative properties, things like boiling point elevation, freezing point depression, vapor pressure lowering, all those type of things is where we commonly will sort of see molality. Not so much the vapor pressure, but the other two. Another sort of unit that is used kind of a lot of times in conjunction with molality, and we'll also see it in the next chapter when we talk about gases, is what is known as mole fraction. And the mole fraction is pretty much what it sort of sounds like. Let's say you had moles of A and moles of B sort of together. So if you wanted the mole fraction, which is abbreviated with that X, you take the moles of what you're interested in. So in this case, we would take the moles of A and we would divide it by the total moles. It is not a fraction or percentage, I guess is the way to say that better. It's not a percentage, so we don't multiply by 100, which means if you add up all the mole fractions, so if we wanted to do it for B, we would take the mole fraction of B would equal the moles of B divided by the total moles. So since, again, it's not a percentage where we multiply by 100, when we add up all the mole fractions, it actually should equal 1, which is essentially 100, but we just don't multiply it by that. And obviously, if we had a mixture of moles A and B to get the total moles, we would just add them together, right? So mole fraction does come up in gases, which we'll see. We'll also come up with sort of molality a little bit later on in that chapter with colligative properties as well. So it's basically kind of like a percentage without multiplying by 100. And it gives you really sort of the percentage of the moles in the total mixture of moles. So why don't you give this a try? Calculate the mole fraction of methyl alcohol, also known as methanol, in a solution that's made up of 0.328 moles of methanol and 0.929 moles of ethyl alcohol, also known as ethanol. All right, so see what you come up with. All right, so we are looking for the mole fraction here. So one thing that we do need to figure out, obviously, is the total number of moles. And that's pretty easily found. We're just going to simply add the moles of our methanol plus the moles of our ethanol. And if we add those two together, it looks like we get 1.257 as our total number of moles. So if we want the mole fraction of our methanol, we would take the moles of the methanol, which is 0.328. We would divide it by the total moles, which is 1.257. The moles will cancel, and again, it will just actually be a number in this case because those units cancel, and we end up with something like 0.261 as our mole fraction for methanol. We also could have done it for the other guy as well, the C2H5OH. Don't want to write H's today, apparently. So we would take the moles of that guy, 0.929, divided by 1.257, and that will get us 0.739. In reality, we actually did not have to necessarily do this calculation to get to this answer because there's only 2 moles, 2 things that make up the moles. We basically could have took 1 minus 0.261, and that would get us 0.739, as the 1 would represent kind of 100%, and you could have got the answer that way. So again, a couple different ways you could get the second one, although in this particular problem, it was just asking for that one. And that is basically mole fraction. So really just a percentage without multiplying by 100. Any questions on that? And if I'm not mistaken, I think that should be it for this chapter. Any questions on any of that stuff that we talked about here in this chapter? Okay. All right, then we are going to roll to the next chapter, which is gases, chapter 8. Again, it should be up there on Canvas if you need it, or with all the other notes, pretty much. Okay, so we got that. Hang on 1 second here. All right, go with this one then. All right, so in this chapter, we're going to talk about gases. So obviously, we're going to have a lot of gas laws. And you do need to obviously know the gas laws, some of which you probably have seen before. Some might be new to you. So let us get going with that. So the first thing we're going to talk about is basically substances that exist as gases under normal conditions. And when we talk about normal conditions, usually that means sort of room temperature. Those are essentially the conditions that you find, for example, in tables where you look up values. So when we talk about that, that means that the pressure is 1 atm. ATM is an atmosphere, and that's sort of a standard unit of pressure. And also sort of room temperature and normal everyday temperature we sort of consider somewhere around 25 degrees Celsius. Now, under those type of conditions, ionic compounds typically don't exist as gases. Ionic compounds are held together by extremely strong electrostatic attraction, and that is a fancy word for the opposites attract. So that's the positive ion, which is our cation, being attracted to our negative guy, which is our anion. And these forces are extremely strong and gets even stronger as the charges get larger. And that's really because, as we'll talk about also in a later chapter, that is what is essentially a intramolecular force. So an intramolecular force is a very strong force that holds sort of an individual compound or molecule together. And typically what happens when we take an ionic compound, and even if we start to heat it under sort of normal conditions of pressure and so forth, typically what will happen is it will just kind of start to melt. It typically will not go into the gas phase, which is really good, right? When we got our salt on our fries, right? Because if it heated up and made a gas like chlorine gas from it, probably wouldn't be very good or fries or anything like that, right? So an ionic compound typically will only start to melt if you've done a reaction where you evaporate off water and you're left with the salt. Again, you can start to see it perhaps start to melt, but it really will not go into the gas phase under sort of normal conditions. Now, when we talk about molecular compounds, which are guys that again are held together by sharing of electrons, so these are guys that are covalently sort of bonded together. The behavior of these guys are a little bit different. There's a lot of molecular compounds which actually are gases under sort of normal conditions. So things like carbon monoxide, carbon dioxide, HCl, which is hydrogen chloride gas, NH3, which is ammonia, CH₄, which is the simplest organic molecule you can have. That's methane, like the stuff that comes out when you like light a Bunsen burner. But a lot of molecular compounds, though, are liquids and solids at room temperatures. But a major difference between sort of an ionic compound and a molecular compound is it is much easier to convert a molecular compound into the gas phase than it is obviously an ionic compound. So as we were just talking about, an ionic compound held together by that really strong intramolecular force of positive and negative attractions, but we can convert a molecular compound a lot easier. The prime example is water, right? So if we take some water, it is typically found as a liquid under normal conditions, but we can take water to the stove, right, to cook some dinner, make some pasta, boil some water. And it doesn't take a tremendous amount of effort to convert, say, that liquid water into a gas like steam to supply some heat. And that is because when we take something like water, which looks like this, we take one water molecule and another water molecule. They are held together by what is known as hydrogen bonding. And hydrogen bonding, although it is a very strong force, it is actually what is known as an intermolecular force. So hydrogen bonding is an intermolecular force, which is, even though relatively strong, is always going to be weaker than an intramolecular force. So an intramolecular force would be, again, if you took one individual water molecule and those bonds that hold that individual water molecule together would be an intramolecular force. That means within the actual molecule itself, as opposed to hydrogen bonding, which is an intermolecular force. And that is a force that holds one molecule together with another molecule, the entire thing. And that is why when we heat something like water and we get to that boiling point temperature, we can convert the water into a gas, because as we heat it, this force here that holds one water molecule together with another is much, much weaker than this intramolecular force that holds the individual molecules together. And we know that's true because if it wasn't true, when we would heat something like water, if the intramolecular force was weaker, we pretty much would get alphabet soup and we would produce hydrogen gas and oxygen gas, which from my limited chemistry experience would mean your pasta would probably never be made in that case. Yes, if you started producing hydrogen gas and oxygen gas while you're on the stovetop cooking it, not a good idea. So what ends up happening though is the bond between one whole water molecule here and another whole water molecule here, that bond that holds those guys together is actually the bond that's easily sort of broken. And when you do, the water molecule goes from the liquid state to the gas state, and it's still water at that point. And again, that's why a lot of times intermolecular forces, which are weaker, is the major forces that we see sort of happening with molecular compounds. And that's why it's much easier to convert these guys into the gas phase. Obviously, when we get into the gas phase, that means that we have everything completely away from each other and they're flying around, right? And as they're flying around in the gas phase and they're moving around and they start colliding with, say, the walls of the container, that's basically what we associate pressure with, right? And pressure is essentially what we associate with gases. So as it says on the bottom there, the stronger the attractive forces between molecules, like the intramolecular forces, the less likely we will see these guys exist as gases under normal conditions. And again, the weaker that force, the easier it will sort of be able to go into the gas phase. Any questions on that there? So some guys that are gases under normal conditions, we have hydrogen, nitrogen, oxygen, fluorine, and chlorine. If you remember, these are all of our kind of diatomic molecules. These are how they naturally come by themselves. They come as twos. That's hydrogen gas, nitrogen gas, oxygen gas, fluorine, and chlorine. Ozone, which is O3, is also a gas, and obviously on our periodic table, group 8, which is our noble gases, they are also obviously in the gas state. Neon, argon, krypton, all the ons. They are what are referred to though as monoatomic, which means they come as ones. They're also the ones that are chemically inert, which means they really don't combine with other gases. They're just fine the way they are. As we talked about bonding, they're very stable, which is why everybody wants to be like them. Those noble gases. And again, in the blue here is all of our guys that we sort of naturally find as gases under normal conditions. So let's talk about some important characteristics of gases. Good talk. Let's go back. Gases, we assume, will take the volume and shape of their container. So because gases are constantly moving around, we oftentimes, as we will see in this sort of chapter, really talk about gases in terms of their volume as the volume of the container they're in. And that is because as they are flying around, they are pretty much filling that container uniformly. Gases are the most compressible state of matter. And as we'll talk about, as you compress a gas, it does have a big effect on pressure. Gases will mix evenly and completely when confined in the same container. Again, just logically thinking about it, we have gases, they are flying around. Just by that process, as they are flying around, trapped in the same container, they are constantly mixing with each other. And so gases are usually soluble in each other because just by the nature of how they are, they're flying around and moving. Now, gases, as we will also see in this chapter, typically have lower densities than liquids and solids. So when we talk about density, and we're going to talk about how to solve for the density of a gas, density of liquids and solids, we usually do it in grams per milliliter or grams per cubic centimeter. When we get the density of a gas, we usually use units of grams per liter. So the units associated with density for gases is a little bit different than the typical units that we use for density. For something that's a liquid or solid, which is grams per milliliter, we typically will do grams per liter in this case. So pressure, which is force over area. And when we talk about sort of units of pressure, there are some common units of pressure that we come across. This is a Pascal, and a kilopascal is also another common unit of pressure. A Pascal is equal to 1 N over M squared. That is a Newton over meter squared. For a lot of what we do, these three guys right here are the common units of pressure. 1 ATM is an atmosphere. mmHg stands for millimeters of mercury. And TORR stands for a torr. And really the reason for those two units have a lot to do with the picture on the right. So one way that we could commonly measure the pressure is by using a barometer. Barometers used to be made out of mercury, although in most of the classes they've taken them out of schools and stuff because it has mercury in it. But essentially what a barometer used to be like, or a traditional barometer, is it is a pool of mercury. It typically will have this column in it, this glass column. And as the atmospheric pressure basically asserts on that mercury, the mercury rises in the tube here. Mercury is an unusual product as well. It actually has a reverse or an upside down meniscus. So the meniscus actually goes the other way. And we still read actually from the top of the meniscus in that case when you would read a barometer. And the reason we get those two sort of units, millimeters of mercury, is because on a traditional barometer, there's usually like a ruler. And one unit that you could read it in is millimeters. Sometimes they're in inches. Sometimes they're in centimeters. And that's really where sort of millimeters of mercury comes from, is sort of reading the level of the mercury in that barometer. The torr comes from the guy who invented it. His name is Torricelli, and his abbreviation for his name basically is another common unit of pressure. He's the guy that invented the barometer. A millimeter of mercury does equal a torr. It's a 1-to-1 relationship between them. And 760 is an important number because that is the number that allows us to convert. So if you got atmospheres and you want torr R millimeters of mercury, you're going to multiply by the 760. And that again will give you torr R millimeters of mercury, which is basically the same unit. And vice versa, if you have torr R millimeters of mercury and you want to convert it to atmospheres, you're going to divide by the 760. And you'll get your atmospheres. So 760, kind of an important unit. It is the kind of conversion factor that we oftentimes will use. Kilopascals, like I said, there's other units of pressure that we come across. PSI, that's pounds per square inch. There's also a bar, right? A bar is another unit of pressure. 1 bar is about, or 1 atmosphere. I'm trying to say that right. 1 bar is like 1.01 atmospheres, I believe. So it's very close to an atmosphere. We're very close in terms of the conversion factor. I would say, again, for us, these three that are circled, probably the most common sort of units that we come across here in gases. When we go above sea level, for example, when we rise above sea level, we do see a decrease in pressure as you go up. And again, why when we are on airplanes, right, everything is pressurized and we're flying above ground. So one way that we can measure a pressure of a gas is to use a manometer. And there's 2 types here. The difference between the 2 is this one is a closed system. So basically it has mercury in it, and as this gas tries to escape, it's got nowhere to go. So basically what it does is obviously push on the mercury. And you can measure the pressure in this case. The pressure of the gas in this guy would be equal to the height of the column of mercury. So that would be how you would measure it. But now you could also do this in this case in more of an open system. And in an open system, same idea. This gas is going to be pushing on the mercury, but you also have atmospheric pressure kind of pushing back down on it. So when we want to find the pressure of the gas in sort of a open situation, you do have to sort of take into account the atmospheric pressure that would be pushing back down on it. So the pressure of the gas would equal the height of the column, just like before, plus the atmospheric pressure that would be pushing down on it, again, because it's basically open to the system. So the first sort of relationship that we're going to look at, and when we talk about gases and gas laws, there's really sort of three variables that we deal with. There's pressure, temperature, and volume. Yeah. So the first relationship we're going to look at is basically the pressure and volume relationship. And we're going to keep temperature constant in this case. And if we look at sort of the relationship that we see here in each of these sort of manometers, we see that over here on the left on A, we have 100 milliliters and the pressure is here. Then we actually start to lower the volume to 50 milliliters. And what we see here is the pressure of the gas starts to increase compared to the higher volume. If we drop the volume even more, we actually will see the pressure continue to rise. So what we see here in terms of the pressure volume relationship is as the pressure goes up, the volume goes down, and vice versa. As the pressure goes down, the volume will go up. And this relationship was one that was sort of discovered, if you will, by a guy named Boyle. And this is basically sort of Boyle's law relationship, is that pressure volume relationship when we keep the temperature constant. And that's what we see here, and that is Boyle's law. If you take a gas, what we see is as the volume gets smaller, as the volume gets larger, the pressure gets smaller. And as the volume gets smaller, the pressure gets larger. And right here is Boyle's law, P1 V1 equals P2 V2. Kind of a before and after condition. And this again is at constant temperature. And again, it's an inverse relationship. So as again, one goes up, the other goes down. And in terms of units, the pressure can be any unit you like, as long as they are the same on both sides. And the same thing with the volume here. The volume can be any unit you like, as long as they are the same on both sides. Any questions on Boyle's law there? All right. So obviously you do need to know Boyle's law. You need to know the relationship. One goes up, one comes down. And again, if you just think about logically what's happening, if I have, say, a volume like this, with my 3 gas molecules flying around, it is going to take longer for these guys to have collisions, right? So the rate of collisions will decrease. And what that means is the pressure will also decrease. As opposed to if I take the same 3 gas molecules and I pretty much drop the volume to there, right? In this particular case, they don't have very much room to fly around, which means the rate of collisions should start to increase. And that means that we should get a higher pressure to occur in that smaller volume. So smaller volume, people don't pretty much have a lot of room to fly around. Higher rate of collisions, higher pressure. Larger volume, more room for everybody to move around. It's going to take longer for collisions to occur, and the pressure should go down. All right, so why don't you try one calculation here. A sample of chlorine gas is 946 milliliters at 726 millimeters of mercury. What is the pressure in millimeters of mercury if the volume is reduced at constant temperature to 154 milliliters? So take a minute or two here and see what you come up with. Okay, so although we've obviously only gotten it so far to one gas law, a lot of times in gas law problems, it's good to kind of write out the information that you find in the problem. So we definitely have a volume that is 946 milliliters. We have a pressure that's 726 millimeters of mercury. We're looking for a pressure, and we also have another volume that's 154 milliliters. So just by looking at that, if you weren't sure, it definitely should point you to Boyle's law. And usually what people do is just kind of go in order the problems. So since this stuff came first, we'll call these guys ones, and we'll call these guys twos. It really doesn't matter the ones and the twos as long as you keep the information that goes together. So you can't like go 726 with 154. You got to keep the right numbers together. We basically have everything here except for P2. So to solve for P2, we would divide V2 to the other side. And we would want to put it in correctly. We do have milliliters on both of these volumes, so that's good. So P2 would equal our P1, which is 726 millimeters of mercury, our V1, which is 946 milliliters, divided by our V2, which is 154 milliliters. The milliliters and milliliters will cancel. We will be left with millimeters of mercury, which is good because that's a pressure. And if we do the math there, we'll call it 4460 atmospheres, not atmospheres, millimeters of mercury here. Any question on that calculation there? Now, sometimes people do sort of mess up in terms of flipping numbers around and stuff like that. So it is good to think about, does your answer make sense? So if we think about what's happening here in terms of our volume, as we go from here to here, our volume is going down, which means we would expect our pressure to go up. And that definitely went up. Yeah, that's a big number. So it definitely went up there. Any questions on that? So again, you can kind of check your answer if you understand sort of the relationship that happens with some of these gas laws, just to make sure you didn't accidentally invert a number or something of that nature. Any questions? All right. So why don't you try another one here? Balloons inflated at 0.55 liters at 1 atmosphere goes to 6.5 kilometers. Pressure is 0.4. Assuming temperature remains constant, what is the final volume of the balloon? So take a moment or two and see what you come up with. Okay, so if we take the same approach here, we have a volume that is 0.55 liters. We have 1 atmosphere, which is a pressure. We have 6.5 kilometers, which is useless information. We have another pressure, which is 0.4 atmospheres. And we are looking for a volume. So again here, if you just kind of pull the information out, it obviously should take us back to our Boyle's law. We are going to be solving for V2 in this case. So V2 is P1 V1 divided by P2. Remember, although it's not a fraction, when you go across an equal sign, things end up in the opposite location. So P2 is on top, it will end up on the bottom when you do that. In terms of units, our pressures are both in atmospheres in this case, so that's okay. So that means that V2 in this case would equal our P1, which is 1 atmosphere, our V1, which is 0.55 liters, divided by our P2, which is 0.4 atmospheres. Again, the atmospheres are going to cancel. In this case, it's going to leave us the volume in the units of liters. And that liters is like 1.4 liters. Again, we could see if it makes sense In this particular case, our pressure is going down, which means our volume should go up. And it did. It went from 0.55 liters to 1.4 liters. So again, it's a good idea to have an understanding of sort of the relationships because it can sort of help you mathematically. Just make sure you didn't sort of mess up that part of it, reverse a number or anything like that. Any question on Boyle's law there? So Boyle's law is pressure volume relationship, temperature held constant. And again, it's an opposite relationship. As one of those variables go up, the other goes down, and vice versa. The next sort of relationships we're going to be talking about is, for example, a volume and temperature relationship, keeping pressure constant. And what we see when we look at that relationship here is at low temperatures, our gas molecules are moving relatively slow. And what we see is we have a small volume. And when we increase the temperature, our gas molecules would be moving faster. And what we see is we have a larger volume in this case. I guess I should put my arrow down there. But what we see in this case, if you're curious, is the mercury part, really badly outlined in both cases here, is the same. So this is basically our pressure part, right? So our pressure part in both of those are the same. So what we see here in terms of volume and temperature relationship is one that was recognized by a good friend, Charles' law. And Charles' law basically says V1 over T1 equals V2 over T2, as we will shortly see. And again, the relationship that we see with Charles' law is as the temperature goes up, so does the volume. And vice versa, as the temperature goes down, so does the volume as well. So they sort of move in the same direction when we talk about Charles' law. And the reason for that is this part of it. They're keeping the pressure constant. So if the volume did not adjust, we would expect the pressure to start to change. So the way in sort of Charles' law relationship that is able to maintain the pressure as being constant is the volume will adjust. So what that means is if we have a smaller volume because the gas molecules are moving slower, that would mean that we technically would not have as many collisions because they're moving a lot slower. So to help us with that, the volume gets smaller, increases the rate of collisions, and we're able to maintain the pressure as being constant. Vice versa, if we're moving our gas molecules faster at a higher temperature, we would expect the pressure to start to go up if the volume didn't move because they would be moving around faster. But the volume is able to maintain and start to adjust. I'll say that right. The pressure is able to maintain and the volume will adjust upwards to allow everybody to maintain the same rate of collisions. And when we look at another relationship, which is sometimes referred to as Guy-Lussac's law, and that is P1 over T1 equals P2 over T2. This is at constant volume. Yeah, so at constant volume, we actually do see that change in pressure that occurs as the temperature increases. So if the volume does not move, it's like locked into place. When we increase the temperature, the gas molecules will be flying around a lot faster, which means there will be more rates of collision. And unlike over here, the volume is going to be locked into place. So we'll have this volume, No matter what happens, it's locked in that place. So our gas molecules at a higher temperature are going to be moving around faster, more collisions, and what we would see is the pressure would go up in that case. And vice versa, if we lower the temperature, our gas molecules would be flying around slower, and we would have less collisions, and we would see a drop in pressure. So these two sort of gas laws are related to each other. One is at constant pressure, and that's Charles' law, which is the way it's able to maintain that constant pressure is the volume will adjust to allow the rate of collisions to remain relatively constant. And Guy-Lussac's law is at constant volume. So because in that case, the volume doesn't move, when we increase the temperature, we see a direct relationship in increasing the pressure, and vice versa. If we decrease the temperature, we see that the pressure will start to drop as well. So those are two gas laws that we should think about. And an important part of both of those gas laws is what we see in this graph. So this is Charles' law. Again, Guy-Lussac's law is the P1 T1 equals P2 T2 at constant volume. And again, this would be constant pressure here. The important part is if you take any gas, no matter what gas it is, and if you do a graph of volume versus temperature, and you extend that line back to the temperature, every single gas hits the exact same number, and that's minus 273.15 degrees Celsius. And perhaps you remember that as that is the number that we use to convert to Kelvin. Yeah? So to convert to Kelvin, that is a temperature in Celsius plus a 273. So if we take minus 273.15 and convert it to Kelvin, add 273.15, we get 0 Kelvin, maybe it's Kevin, 0 Kelvin, which is sometimes referred to as absolute zero. And it was Kelvin that sort of recognized this. That's why it used to be called the absolute temperature scale. Later, obviously, renamed for Kelvin. And essentially, the good news of that, which is probably not good news, but the bad news of that is if you're doing a gas law and there's temperature, it always needs to be in Kelvin, no matter what the deal is. Every temperature and every gas law, including this one here, does need to be in Kelvin. Yeah. So it's a safe bet that if you're using some type of gas law, you should be converting that temperature into Kelvin before you go into the gas law. Now, even if, which is a very common sort of situation, even if they give you the temperature in Celsius and they ask you to give the answer in Celsius, people sometimes when they do that think, oh, it's all good. They gave it to me in degrees Celsius. I need to answer in degrees Celsius. I could just leave it in degrees Celsius. And you can, but you'll be getting a big X probably on that question, and you would get the answer wrong. So even if they give you the temperature in Celsius and ask you to calculate it in Celsius, you need to convert it from Celsius to Kelvin. You need to go into the gas law and then convert it from Kelvin back to Celsius. So you want to make sure that you do that. So any questions on those two laws there? Okay, so I think what we will do is stop here for today. It's like we're getting to the end. All right, any questions on stuff that we talked about today before we talk about what's ahead? The weekend, I think, is ahead, but other than that, we'll talk about some other stuff that's ahead. Any questions on anything we talked about today? Okay, so then let's talk about stuff that we got going on. I believe today you have two things that are due. You have experiment 9 and study assignment, I want to say F, which is that redox stuff that you should have hopefully been doing. On Tuesday, I think study assignment G is due, and that's the stoichiometry one, which obviously you should be able to complete at this point. Starting next week on the 5th of May, it's May already, look at that. The 5th of May, and next week we will start the titration experiment. So starting on Tuesday, the titration experiment will be up for you to start. And we'll technically be doing the titration experiment all of next week. Also on the syllabus scheduled for next Thursday is an exam, which we're not going to take next Thursday on the 7th. We're going to move the exam to May 14th, 1 week later. So I believe exam number, I guess that would be 3 for us, yeah. Exam 3 will be on May 14th. That will give us the opportunity next week to finish this chapter, which is the gas chapter, because that will be on the exam. So the exam coming up will be all the stoichiometry stuff, I believe, titration stuff, stoichiometry stuff, the redox stuff, and I think it will be here the gases. And so that will be what will be on exam 3. So exam 3 is moving from the 7th to the 14th. Any questions on that? And I think that our exam 4 will then be where it's scheduled, which I think is May 26th, if I'm not mistaken, somewhere in that area. So exam 3 will be on that Thursday. We'll finish lecturing on this chapter next week, obviously, and continue on to the chapters after that. We will start the titration experiment officially on this coming Tuesday. And again, your study assignments and experiment due today, I believe, and one due on Tuesday. Any questions on anything that's happening or coming up? And in the next day or so, I will put out an announcement on Canvas. Yes, next Tuesday, which is the titration experiment, is experiment 10, I believe. And it technically is going to be a formal one, so you'll watch a video, obviously, but usually it'll take a few days for us to physically do it. So all of next week, which is when it's scheduled. We're scheduled to start this week and next week, so we'll just do it all next week, and it should be experiment 10. Other questions? All right, so that will be it for lecture today. I'm going to take a break, maybe a 15, 20-minute break. I will open up the lab section in case you do have some questions. You're welcome to stop by. Again, I don't know if I'll be there, obviously, until 10 or whatever. We're usually there, but I will open it up probably in about 20 minutes or so, about maybe 7:20. And if you do need to get there to ask questions on any of this stuff, make sure you go through the lab link for that one, okay? Other than that, if there's no other questions, we will stop here today for this lecture. Have a good weekend and all that good stuff. And again, if you do have questions, about 6:20, the lab will be open.